Okay, well, last time we took a look at the general monitor, and we used the classification scheme that Bohr came up with, and we looked at how the binary monitor is classified and how the Java monitor is classified. And the last assignment for the course is to use monitors to solve to do some algorithms. And so what we want to look at now is the code. So we're going to look at some C++ code and some Java code to see how you do monitors in these two different languages. Okay, so the first problem that we're going to look at is the producer-consumer problem with a finite buffer. So you've already actually done this one with semaphores. Do you remember this one? It's the circular queue, and you have a producer and a consumer. And so now, and what's the idea of a monitor? The idea of a monitor is that you consolidate all your critical section code into monitor methods. Yeah? And what are these monitor methods guaranteed to be? A monitor method is guaranteed by the monitor to be what? Atomic. No interleaving. Okay? Now, a process might get suspended. If a process executes wait, it might get suspended, but because it's a first in, first out, it's not going to get, well, it shouldn't get interleaved. Okay? There's only one. You can't have two monitor methods executing at the same time. All right, now, so the way we're going to solve the producer-consumer problem with the finite buffer is we've got two condition variables, not empty and not full. Now tell me, in a monitor, every condition variable has what associated with it? A queue of what? Processes that are blocked. A queue of blocked processes. Okay, so there's going to be a queue for not empty, and there's going to be a queue for not full. Is everybody with me on that? Okay, and now the producer is going to call append D. So now what we're going to do is, instead of writing the code for append in the application, in the main program, we're going to write that code. The append is going to be a monitor method. Is everybody with me on that? The code's going to be a monitor method. So the producer calls append D, and only the producer can be in the not full queue of blocked processes. Because how can you append? What do you have to make sure of when you do append? When you append, you have to make sure that the buffer is not full, okay? So you have to wait for it to be not full. You might have to wait for it to be not full. And then the consumer calls the method take, right? And take returns a type D, right? Append, we give it a D, and then take returns a variable of the same type that D, the data type. Okay, and only the consumer can be in the not empty queue, because what does the consumer have to do? The consumer cannot take, in the same way that the producer cannot produce something and put it on a queue that is full, the consumer cannot do what? Yeah, cannot take from a queue that's from a buffer that is empty.
And append and take are monitor methods.
And append and take are going to be monitor methods. That's the idea. So given that they are monitor methods, here's algorithm 7.3, the producer-consumer with a finite buffer and a monitor. And look how easy it is. There's no semaphores, there's no nothing. P1 is D gets produced, so it just it's producing the data, and then it just calls append. Okay, pc.append. PC is the monitor. Okay, so pc.append. PC is producer-consumer, right? So, and he calls producer-consumer append. And then what does the consumer do? Loops forever, and what does the consumer do? D gets pc.take. So notice that the pc.take returns, it's a function that returns, it's not void. Okay, so D gets that, and then the consumer does whatever the consumer wants to do with that data. So see how easy the main program is? Everything's all consolidated into the producer-consumer monitor. But of course, now what do we have to do? we have to write those methods in the producer-consumer monitor. Now I put this some bold horizontal lines here to distinguish visually where append starts and ends and where take starts and ends. And so this is monitor PC. So PC is the name of the monitor, which stands for producer consumer. And this, by the way, is not, this isn't C++ yet. This is that abstract language independent code that he uses in these boxes, right? We'll take a look at the C++ code in a minute, as well as the Java. We'll translate this to C++ in Java. So now look what he does. Now what happens is so we have a buffer, and it's initialized. So we have the lowercase b buffer is initialized to empty. So the buffer is in the monitor. That's one of the data structures in the monitor and this could be a circular. It's going to be a circular buffer. Okay. So that's allocating the buffer, and then we have a condition variable called not empty, and we have a condition variable called not full. Yeah. Is everybody with me on that? And what can we do with not empty? What can we do with each one of these? We can do a wait C and a signal C on each one. Now let's take a look at how at our append. So our append takes V, that's value of type data type, right? And in order to append, like when the main program calls append, what do we have to do here? We have to check if the buffer is full. So we assume that the buffer is full and is empty that we can check, right? So if the buffer is full, what do? We call what? Wait C, not full. So if it is full, what will happen? Wait C always does what? It always blocks, right? It always does, right? That's the difference between wait for a semaphore and wait for a monitor, right? So, and now look at here, you guys. Notice here that wait C is in the body of an if statement. This is because of this is because of Ben-Ari's definition of a monitor, of his monitor behavior. So we don't need a loop here. Wait C is in the body of an if, right? And then we assume that eventually an item will be taken from the buffer, and when that item is taken from the buffer, the buffer will not full will be false. And so after we've done our waiting, we can assume that we can append. So we append V to the buffer, and then we signal not empty. And this is a signal C and a wait C. And signal C, notice that the signal C is the last statement of the operation. We want to use that idiom. It's so that everything will work correctly. Because once you do a signal C, then we're going to quit. We're going to terminate, right? And nothing can. So if there was some code after this signal C not empty, then that might make it, empty again. See. So we're going to signal C not empty, and then operation take is just the opposite. So we have this local variable of type W of type data type. And if the buffer is empty, what do? Wait C not empty, and again, that's wait C is in the body of an if, and then W gets the head of the buffer, and then now that we've taken something out of the buffer, we know it's not full, so we signal C not full. And here again, signal C was the last statement. This signal C is the last possible statement of the operation because this returns something. So we can't have the return here, right? Otherwise, because return returns. Otherwise, signal, would never execute. So anyway, so signal state is the last possible statement of the operation. We return W. All right? Okay, now let's take a look at the Java. So here is the producer-consumer problem with a finite buffer. Now, you got to keep in mind now here that we can't do everything all in just one file, because in Java, the convention is that each class has its own file. Now, those of you who did the big Java project last year recognize this, right, when you did the assembler project. And we used NetBeans to manage all of those multitude of files. And so that's what we're going to do here as well. So here is a list of the 4 files, each file with a class. The first file is BA listing 0703.java for the main program. And then there is a PC monitor.java for the monitor itself. And then there is a producer.java for the producer and a consumer.java for the consumer. Now, here's what we have to, here's the design problem that we have to solve. We have to, what we want is for the monitor has to be accessible to the producer and the consumer. Is everybody with me on this? The monitor has to be accessible to the producer and the consumer. Because after all, the producer is going to call the method to append, to append the data, and the consumer is going to call the monitor to take data. Yeah? So there has to be some way, but on the other hand, they are their own separate classes. Do you see what I mean? They are separate. And so we have to figure out a way, we have to design a way for them to be able to communicate with this common monitor. And so just keep that in mind when we look at this code. So here's a rundown of what the main program is going to do. The main program allocates the monitor. Actually, let me do a little graphic here. Okay, so here's the main. Let's just let this box be the main program, right? So this is our main. And what this is saying is that the main program allocates the monitor. So, but now, all allocation is done with new, right? So where does new, which part of memory does new get its allocated storage from? The what? Anytime you do new, where is it allocated from? Come on, you guys. Yeah, from the heap. Okay. So, so the heap, actually the heap is out here in Never Never Land, but it's sort of like outside this main, but I'm going to draw it in here anyway. Okay, so the main program allocates the monitor. Actually, no, we're going to allocate it out here. The main program is going to allocate the monitor. So then it's going to allocate this monitor here, right? And then it's going to allocate the consumer, passing it a pointer to the monitor so the consumer can access the monitor. So then it's going to allocate the consumer here, and then it's going to allocate the producer, passing it a pointer to the monitor so the producer can access the monitor. So this is going to be the producer. Actually, let's do it like this. So for now, we're going to fill this in when we look at the code. So for now, here's the main. This is going to be the buffer. This is going to be the consumer. This is going to be the producer, right? And this is a high-level description of what main does. Allocates this, giving it a pointer to this. Allocates this, giving it a pointer to this. All right. So let's see how it does that in the code. Now watch. So now let's do a little code walkthrough of main. So this is BA listing 0703, and you can see the open brace here and the closed brace here. Now watch what it does. Public static void main. We're not going to use the arguments, okay? The command line arguments. So now what does it do? It does PC monitor, capital PC monitor, it's producer consumer. Lowercase PC monitor gets new PC monitor. So now what that does, what that says is that there is a PC monitor here. We can draw it like this. All right? Now I know that in Java there is no explicit pointer type, but all variables in Java are called, do you guys know this? All variables in Java are called reference variables. Have we talked about this before in our project? Reference variables. Okay, so there's a clever little saying. It says there are no pointers in Java, but in Java everything is a pointer. So what that means is that there's no explicit pointer type in Java, but on the other hand, every variable is a pointer to something. Okay, except for the primitives, except for a special case. All right. So anyway, this is a pointer. So here. When it says PC monitor, so this is our variable. This is our variable PC monitor. This is our variable PC monitor, and it's pointing to this. And this is a PC. Well, this is a pointer to this, and the type of this is a capital PC monitor. Are you with me? And does everybody see that this graphic shows what this does? This PC monitor gets new PC monitor. Are you with me? And now what does this do? This does consumer, capital C consumer, lowercase c consumer gets new what? It's new what? Consumer. But it passes what? This PC monitor to the consumer for its constructor. Are you with me? It passes that for the constructor. Okay? So actually let's do now, let's jump ahead to the consumer code. So we're jumping ahead a few slides to the consumer code. And let's take a look at what the consumer has in it. First of all, consumer extends thread. And what does it have in it? A little what? A private variable named what? PC monitor that is of type what? Capital PC monitor. So what that means is that the consumer, so this is the consumer. Let's write this here, consumer. And this is the producer. This is going to be the producer. But now look, what is the consumer going to have in it? It's going to have its own little what? PC monitor variable in it. And furthermore, what is this constructor going to do? What does it do? It does this.PC monitor gets PC monitor. So what does that make this point to? What does that make this pointer point to? The same thing this is pointing to. Are you with me? That's pointer assignment. Are you with me on this? Because we know C++. So there's its little PC monitor pointing to this one. Yeah? And now let's go back to the main program and see what it does next. Well, it does consumer.start. Let's skip over that for a minute. So the consumer starts up. Interesting how the consumer is starting up first. But doesn't the producer have to produce before the consumer can consume? That's all right, because our monitor takes care of, yeah? Okay. So now what do? Producer gets new. So now capital P producer is the type, and then lowercase p producer is the variable, or the object, gets new what? Producer PC monitor. So if we skip to what the producer is, it's the same kind of thing, right? So here's the producer, and what does the producer have in it? A little local what? Make this a little bit bigger. It has a little local what? Variable named PC monitor. And what does it get? It gets this PC monitor that got passed to it, and this then is pointing to this. Does everybody see? So the consumer and the producer, they have access to the monitor through this PC monitor pointer. It's a reference variable. They refer to it's really doing pointer assignment, but Java people don't like the word pointer. So if you're around some Java aficionados, don't say pointer. Say it's a reference variable and it references the same thing. But whatever. See what I mean? I mean, people get all excited about stuff like that. All right, and then it does producer.start, and then the producer starts, and then we have our usual try consumer.join, producer.join, and then catch, boom, boom, and then does everybody see how that worked? I mean, how the main program works. All right, now let's see now let's take a look at the PC monitor. Okay, so now in the monitor, yeah, I don't have a block here for the. Oh yes, I do. I have a block. Here's the PC monitor. So here's the block for the PC monitor. So inside here, there is code for what? For append, you see, and for take. So that's the append and the take that we looked at before. Yeah, and so what do we have here? Now, okay, so final int, that's the Java way of saying constant. Yeah. N is 5, and here we have int oldest gets 0, newest gets 0, so we initialize right here instead of using it in a little init section. And then volatile, little review for the exam here. What does volatile mean? What does volatile mean? I think we even reviewed this once before. Come on. What? No, static is 1 per class instead of 1 per object in C++, and in Java actually. What is volatile? It tells the compiler to not do what? Change? No. Oh, come on, you guys. Oh. It does not optimize away the what? The loads and the stores, so that you can analyze your code, without making sure that each line is completed before the other one starts, right? So if you have any limited critical reference counts, you can make sure that they all are analyzed correctly. Okay, so and this count is going to be that's in the monitor. Okay, so it's an attribute of the monitor. So we have volatile int count gets 0, so count is initialized to 0, and then here's int buffer gets new int, and so that's how you do array in Java. Now look, anytime you have Java, what you do is, and we saw this before, because of the way the entry precedence is equal to and not less than the wait precedence, the waiting processes have to loop on their conditions, because so you have to say while count equals n, try, and then wait. Yeah? And so the waiting processes, they have to loop. So this is not an if statement, this is a while statement. So it's while count equals n, try, wait. Yeah? And then here's the code that's like the other. Buffer newest gets v, newest gets newest plus 1, mod n, count gets count plus 1, system.out.println, producer put v, and then notify, and then the signaler executes notify all. So that's what we had seen before. So this is in a loop, and this is notify all. And it's the same kind of thing for take. The while count equals 0, try, wait. So this is in a while loop instead of in a if statement. And here again, the signaler executes notify all. So you see how to do the translation into Java. So are we good? And now here is what the producer does. Now, so when the main program called start, what does start do? it made the, where did it put the, it created the process by doing what? It created the process by doing what? Making a what for the process? Oh, good. It's by making a process control block for, and putting it where? And then putting that process control block in where? Where does it put it? Which queue? Yes, good. In the ready queue, so that it will be picked by the scheduler. And then when it's in the ready queue, it's the statements inside the run that execute as it's going in, being scheduled in and out of the running state. Is everybody with me on that? Has everybody got a good picture of that? Okay, and so now what does the producer do? What we have this producer do is looping 15 times. And now, of course, because we're in Java, we have to have all these delay statements because, you know, otherwise we won't know if it, you know, but hopefully it'll still work, you know. So we're going to put these delay statements right in here, and here's at random between 0 and 59. Actually, and then, yeah, sleep delay. And now what does this producer produce? This producer produces 10 times I, okay? We only have one producer here, and then this producer is finished. And then here it's, look at how the code is so similar. Here's the producer code, now look at this slide. There's the consumer code. It's the exact same thing, only the consumer started, and then here's what the consumer does. Loops 15 times and gets that. All right. And maybe we can finish up with a demo of the Java version. This time it's only just going to go from 0 to 15, 0 to 14. Okay, so here's our demo. We see here is we're in algorithm-7-3 in IntelliJ here, and so here are the 4 files. Here is the class algorithm 0703 with our PC is the name of our PC monitor. This name was slightly different than the video that we just looked at. I think we called it PC monitor, but now we're calling it PC. So that's algorithm 0703. Here's the consumer. And notice, by the way, that this is the same package. Algorithm 0703, that's the same package as our algorithm 0703. See, here's they all have the same package so that they can be compiled together. And here is the PC monitor with our final int n gets 5, int out 0, in 0. And here's the append method, and here's the take method. All right, and here's the producer code. So let's give it a run. So we need to execute algorithm 0703 here, so we'll put algorithm 0703 here, and we'll run it and see what happens. And here is the run. Oops. So let's see how so the consumer started, and even though the consumer started before the producer, that's all right because the consumer had to wait until the producer put something. So the producer put 0, and the consumer got 0, and then producer put 10, and then 20, and then 30, and then finally the consumer got the 10. Then it got the 20, and then the producer put the 40, and etc. And so you see we programmed it so the delays so that the producer would produce a little bit more than the consumer. And so at the end, the producer finally put 140, and then the consumer cleaned things up by consuming 100, 110, 120, 130, and 140. Let's run it again and see if there is much of a difference. a little bit of a difference. Here again, the consumer started first but had to wait, and then producer puts 10 and 20, the consumer gets 10, the producer put 30 and consumer got the 20. So the consumer is kind of keeping up with the producer here at the beginning. Producer put a couple more, the consumer got one. This time producer put 60, 70, 80, 60, 70, and 80. And then the consumer got the 40, and you can see how everything works great. And in the end, the consumer got the last 140. All right, end of demo. So let's take a look at some C++ code for the implementation of the producer-consumer problem with a finite buffer. So here's the code for class PC monitor. And again, we're using Mesa semantics where E is less than W is less than S so that the signaler has the highest priority precedence. And we start off with our constant n initialized to 5 or set to 5. That's how many items will be in the buffer. And we have out and in, which are both integers, to keep track of for our enqueuing and dequeuing. And we maintain this count, which is an integer, which is a count of how many elements are in the buffer. And then our int buffer n, which allocates a buffer with 5 elements subscripted from buffer sub 0 up to buffer sub 4, 0, 1, 2, 3, and 4. And next we have our PC mutex, which is our mutex to guarantee that the methods of the buffer are executed atomically. And here's our 2 condition variables. So we have this C++ condition variable type, and we have one for non-empty and one for non-full. So now here is the code for method append. And so as we did before, we have a mutex, a unique lock, because we're going to use a condition variable, and with template type mutex, and we give it, and we have our local variable guard, which uses the that RAII coding pattern, which gives the lock our PC mutex for mutual exclusion of the append method. And here, again, as we did with the implementation of the counting semaphore, we have not full is the condition variable, and it can execute this wait, and we give it our guard, and our condition is return count not equal to n. So as before, this provides us with the automatic while loop. The automatic spurious wake-up loop is specified in the C++ semantics for wait. So that's programmed behind the scenes, and we don't need to see it. And then buffer sub n gets v, n gets n plus 1, mod n. Count gets count plus 1 because we put something in the buffer, so the count goes up by 1. We have a little output statement here to stream out. And then we empty with the way that C++ does signal is with the notify 1 statement. So that's all pretty straightforward. And here is the code for take. Again, we use the same PC mutex linked to our guard for the RAII coding style. And our not empty dot wait, we have the guard, and our condition here is we return count not equal to 0. So we have, again, that automatic spurious wake-up loop programmed for us by the C++ programming language, so we don't need to actually write the loop ourselves. And here we have int local variable temp gets buffer sub out, so there we are consuming. Out gets out plus 1 mod n to take care of the consumed item, and we decrease count by 1. And then we have a little output statement here, consumer got and what the consumer got. And then for the signal again, same recipe, not full dot notify 1, and then we return temp, because take takes an integer and it returns that integer that was consumed.
So here's the code for the producer run. And again, we just loop 15 times, throw in a random delay just to try to make things interesting there. And what we produce is 10 times I, and so that's what we append. We do our pc.append, which appends that to the buffer. And then after that executes 15 times, we output producer finished, and similarly for the consumer run. So all that's pretty straightforward. And then here is our main program, very simple. We have thread consumer, and we tell it to run consumer run, and we have a thread producer, and we tell it to run producer run. And then we do the usual consumer.join and producer.join, and then we return exit success. So that's the code. Now let's take a look at a little demo to make sure this works. Okay, so here's our demo. So here's the code for PC monitor that we saw on the slides a few minutes ago. Here are the condition variables, not empty and not full. Here's our append. Here's our take. And here, our PC is a global variable. Lowercase pc is our global variable, which is a capital PC monitor type. And here's our producer run, and here's our consumer run, and here's the main program. All this code that we looked at just a minute ago on the slides. So let's come up here and select our project that we want to run, which is algorithm 7.3 on the CLion IDE. We're no longer using NetBeans, by the way, in case you didn't notice. And let's give it a run here and see what happens. And sure enough, it looks quite similar to the producer-consumer run that we did with the Java program. Let's see here what happened. Consumer started first, then the producer started. The consumer got blocked until the producer put... Oh, it looks like the producer put a couple of things in the buffer this time before the consumer got the first one. Then the producer put two more items in, and then the consumer got one, and then the producer put 40 in, and then finally the consumer gets the 20, and then puts the 50 and the 60, puts the 70, then the consumer winds up getting the 30, and so on. So it looks like it's behaving quite nicely. No bad behavior here. Let's run it one more time and see if it starts off the same way. Put 0, put 10, got 0, put 20. Let's do it one more time, see what happens. I think it's a little bit different. Yeah, this time we put 0 and we got 0. The consumer got the 0. And then we put 10 and 20, and then the consumer got the 10. So you see a little bit of unpredictability there, but everything works as it should. In the end, the producer finished, and then the consumer got all caught up. Looks like the consumer got the 130, and then the producer put the 140, and then the producer finished, and then the consumer got the 140, and then the consumer finished. So a nice little demo of the producer-consumer problem with a monitor using the C++ Mesa semantics. Good deal. End of demo.
Now, I want to just do one more example. This is a very interesting approach to the dining philosopher's problem. I'm not sure. The problem is, even though this is clever, it has a small problem. But here's what this here's another approach to the dining philosopher's problem that is in our book. Okay, first of all, remember how we had fork sub I when you did the dining philosopher's problem, and fork sub I, that was a semaphore for the fork. Now, this fork sub I does not represent a fork. This fork sub I represents, the I in here represents philosopher sub I. And I actually think that I think you had an idea when we were first encountered the dining philosophers problem, do you remember you said, have them be able to pick up 2 forks at once? Do you remember that? And with no interleaving between picking up the first fork and the second fork. And we kind of thought about that might be a way to do it. This is actually that. What this solution does is it makes it so that it's a monitor solution, and it makes it so that a philosopher picks up, it's atomic to pick up both forks. Do you see what I mean? Instead of like picking up the left fork and then picking up the right fork, the philosopher picks up 2 forks at once in an atomic operation, because all the methods in a monitor are guaranteed to be atomic. But now look, fork sub I is not an element for fork sub I, for the ith fork. It's an element for the ith philosopher. And the meaning of fork sub I, it's unfortunate that he gave this the same name, fork. We should have called it something else. But now, in this particular problem, fork sub I is how many forks are available to philosopher sub I. So you see, if I'm sitting here, and there's a fork to my left and a fork to my right that are available, then fork sub I is 2. Do you see? If the fork on my left and the fork on my right, then fork sub I is 2. If the fork on my left is not available and the fork on my right is, then fork sub I is 1. And if neither of them is available, then fork sub I is 0. Do you see what I mean? So to understand this, you got to understand this. Okay, so it's initialized, and furthermore, all the fork sub I's are initialized to 2 because 2 forks are initially available.
This is not.
So here's what happens. Before eating, we have a monitor method that's going to pick up the 2 forks at once. So before eating, what we do is we decrement the number of forks available to our neighbor on the left and the neighbor on our right by 1 each with no interleaving. Do you see what I mean? We subtract 1 from, so if I am philosopher sub I, then when I try to eat, when I try to pick up my forks to eat, what I do is in one indivisible operation, I subtract 1 from my left and 1 from my right, the forks available on the left and forks available on the right by 1. With no, and because it's a monitor, there's no interleaving. It's atomic. So look, here's the solution. Check this out. It's really clever. Maybe we should see if we have a... Yeah, here. Before we take a look at the solution, let's take a look at the code for philosopher sub I. Philosopher I. What does he do? Loop forever. Think. And then he does take fork sub I. Now, what is I? That I is me. That's the index for philosopher sub I. And then eat. And then release forks sub I. So we just do that over and over and over again. Okay? And now look, what is the code for this? So here's the monitor, it's called fork monitor. And we have an integer array, 0.4 of forks, and initialized to 2, 2, 2, 2. Yeah? Okay? So all these are initialized to 2. And now what's our condition variable? Well, our condition variable is called OK to eat. Now, what's associated with OK to eat? A queue of blocked processes, right, is associated with OK to eat. And so there is an OK to eat sub 0 for philosopher 0 and an OK to eat sub 1 for philosopher 1. So how many queues are there here? There are 5 queues. Does everybody see that? Because this is an array of condition variables, so it's an array of... So do you see that there is a queue for every philosopher, a separate queue for every philosopher? Do you see what I mean? Instead of just one queue for everybody. Are you with me on that? So you think associated with each condition variable is a queue of block processes. So now look, so check this out. So operation take forks. So we do take forks integer sub I. So now what is the first thing that happens here? If fork sub I is not equal to what? 2. So I got to have 2 available, right? Now, if fork sub I is not equal to 2, then atomically we do what? Fork sub I plus 1 gets fork sub I plus 1 minus 1, and fork sub I minus 1 gets fork sub I minus 1 minus 1. So we subtract 1 that's available to my neighbor on my left and the neighbor on my right. Are you with me? And that happens atomically. But if fork sub I is not equal to 2, what do? Wait C, okay to eat I. So now I go into my own little personal queue of blocked processes, and that only I can be in there because there's 5 of them, 1 for each philosopher. Do you see what I mean? So he's blocked in there. And now, whenever you release a fork, what do? Operation release forks integer sub I. Fork, so what do? Oh, and I'm going to tell my neighbors that they have 1 more fork available. So fork sub I plus 1 gets fork sub I plus 1 plus 1. So that's, I increment how many forks are available to the neighbor on my right, and I add plus 1 plus the number of forks that are available to my neighbor on my left. And then, if fork sub I plus 1 equals to, after I've done that, and this is all, there's no interleaving, after I've done that, then what do? I signal C, I signal, in case that philosopher is waiting in his individual queue, I signal him, and I similarly signal the guy on my left. Pretty clever, huh? There's only one problem. A slight problem. This solution has mutual exclusion and is deadlock free, but yuck can starve. And our author, I don't think I want to go take the time because we're a little out of time now. But here is a scenario for starvation of philosopher 2. As that turns out, philosopher 2 can be blocked in his own little queue indefinitely, and there's a scenario for which that happens. And so here again, this is a situation where what seems obvious, I mean, on closer inspection, you can be close but no cigar in terms of starvation. So this happens to not be starvation, but it's a clever approach, and it's an interesting analysis, interesting way to analyze. Okay, good deal. See you next time.